Hello and welcome to this AQA Further Math Statistics video, the third in the series looking at confidence intervals. So a quick reminder of what we looked at when we found confidence intervals for an unknown population mean in the previous video. The confidence interval provides a range of values for that unknown mean, and it also has an associated level of confidence. And the formula we used is simply x bar, the sample mean, plus or minus z, and z relates to the level of confidence involved, multiplied by the known standard deviation of the population, divided by root n, the sample size. So what do we mean in terms of large samples? So this video is going to focus on what happens in a particular situation when we have a large sample. So this video is focusing on what happens with large samples. So if we imagine our population with unknown mean mu, and perhaps now this time just consider unknown variance as well. If we take out our sample, how are we going to work out something about the unknown population mean when we don't definitely know what the population variance is either, and that possibly is quite a common scenario. And for a large sample, the standard deviation of the population can be estimated by that obtained from the sample data, the S standard deviation, the n-1 divisor standard deviation. And generally, n greater than or equal to 50 is a large enough sample so that we can use our estimate for the population standard deviation, S, from our sample, in order to get a reasonably accurate confidence interval for our unknown population mean mu. And just before we move on to look at the actual formula, remind you of that. Also a quick reminder that we may also have a situation where we don't know the distribution of our population. It's not necessarily normally distributed, and remember the central limit theorem tells us that as long as the sample size is greater than or equal to 30, not greater than or equal to 50, so obviously greater than or equal to 50 encompasses the central limit theorem very easily, we know that the distribution of these sample means will always be normally distributed. And this is just an excerpt from the formula book. I've added in an extra formula here, so make sure you're familiar with the information on this page. That's all relevant to what we're doing at the moment. And if we want to estimate the value of the population variance, we use S squared, where this is the formula with the n-1 divisor. This is probably a slightly more user-friendly version if you're given perhaps sigma x squared and x bar squared as summations in the text of a question. If you're just given a whole list of data, then put it in your calculator and simply obtain S and x bar to use for finding your confidence interval. So what's the formula? Well, to remind you of the formula that we used before, we didn't worry about the size of the sample. We always had a normally distributed population, and we always knew the population standard deviation or variance. In the case we're going to look at here, we're going to have a large sample, and in that case we may or may not know that our population is normally distributed because it won't actually matter. We can use the central limit theorem if we don't know that, and the population standard deviation or variance in this case is not known, so in the formula, rather than with sigma, we're going to use S, our estimate from our sample of the population standard deviation. So there is an example here, and thinking about all of those facts about large and small samples, about random samples, about the distribution of our population, just take a moment, perhaps pause and read through this question and think what information we've been given. So if we read through, we are told that we have a random sample. Well, that's excellent because we either must know or assume that our sample is random in order to evaluate a confidence interval. We can see that we are looking at 100 customers, so we have a large sample, clearly greater than 50. And that means that S, which we're given, which is the estimate from the sample of the population standard deviation, that's a perfectly valid estimate to use. They've also helpfully given us X bar, so we have these summarized results to use. But also notice that we don't know anything about the distribution of the original population, the amounts of money being normally distributed, but actually that doesn't matter because the central limit theorem will tell us that X bar will be normally distributed anyway. So having established all of those facts, now all we need to worry about is the fact that we want a 90% confidence interval. We need to find the z-score corresponding to that, and hopefully you're quite happy that minus and plus 1.645 will give us 90% of the z-scores between those two values, and therefore our 90% confidence interval for mu is just X bar plus or minus Z multiplied by S over root n, and you should be able to obtain that answer there. So on this page is what looks like quite a complicated flowchart, but it's really worth thinking about it. First of all, notice that I have said random samples. That's the first thing to check. You need to check whether or not your population is normal. You need to check whether or not you do or do not know your population variance or standard deviation. So, for example, in the first video, we had a normally distributed population. Yes, we knew, yes, what the population variance was, and we just found Z and used that value to find our confidence interval. If we don't know what the population variance is, now we know if we've got a sample greater than or equal to 50, we just evaluate S squared to use to estimate sigma squared and find Z as before. If we don't have a large sample, then we in fact have to use something called the t-distribution that you'll be looking at in later videos. If we follow down this side, if we don't know that our population is normally distributed, as long as our sample size is greater than 30 and we know our population variance, then we can just proceed as before because of the central limit theorem. If we don't know that it's greater than or equal to 30, then we've reached a dead end. And similarly, if we don't know the population variance, as long as our sample size is bigger than or equal to 50, we can again find our estimate and proceed as before. If that's not true, then we can't go any further. So to just summarize, these are our two formulae that we're using in those two different cases where we know the population variance or where we have a large sample and we don't know what it is. And that concludes this video.